let's do a real quick roll check. All teammates here from Aggie MedTech?
Yes.
Yes. Everybody here from Ray-Bans?
Yeah.
RDS?
Yeah.
Sixth Sense?
Yes, sir.
Yeah.
I'm ready.
Comex?
Yep.
And Team Z. They're so secretive we can't even know the name. All right, before we get started,
It's the name.
students, we need to say some thank yous. The first person we need to say thank you to, if you please stand, Mr. Eric Hall, who came up with this idea. We need to say thank you to Stephanie, Sarah, Bianca, Jasmine, Professor Fred, is Professor Janine here?
No, it's not here yet.
Oh, and then Professor Randy. Let's say thank you to the team that's made this all happen. I would say we need to thank our sweet custodian, but we were able to do that last night. We had a birthday, so we had a birthday cake, and we're able to thank Tiffany because she's thebomb.com. Now I'd like to introduce you to the judges. You know their names, but I'd like them to stand, tell you just a little bit about themselves. Let's start with you, Mr. Hall.
My name is Eric Hall. I'm a first-year medical student at Texas A&M InMed, and won this competition in the spring to present this problem. It's something very near and dear to my heart because I'd like to one day work with these machines, so maybe I can use one of your solutions in the future.
Howdy, I'm Saurabh Biswas. I'm a faculty in biomedical engineering, and also I work in Texas A&M Engineering with innovation and startups. So my background has been in medical devices almost close to 2 decades. So what you are doing today, certainly I have been living this for a long time. It is very difficult to take ideas from product to market, and I lived that through multiple different products. So what you are learning today is very, very relevant to what you all might be doing in whatever different fields you go. So this is a great experience. I wish you all the best. And I'll be very happy to mentor you, help you after you complete today's process. And if you want to keep moving with this product or the idea, I'll be very glad to help you with that. Okay, thank you and wish you the best.
Howdy, my name is Harry Hogan. I'm a faculty member of mechanical engineering, but also went to the dark side a few years ago and work in the dean's office now. And that title, Senior Associate Dean for Academic Affairs. I got all the words right. What that means is I get to work with undergraduate and graduate academic programs and curricula and those sorts of things. But also, I get to work with the what I call enrichment and extracurricular activities that are located, particularly those that are located here in Zachary, like the Student Engineers Council, like entrepreneurship, like the honors program, like global programs, Zachary Leadership Program. I'm not naming them all, but that's another thing that I really enjoy about the job is being aware of and involved in a little bit programs like the one you're participating in, and it's even more fun to be here and actually spend some quality time with you, and look forward to hearing from what all you've got to share, and congratulations already on what you've already accomplished throughout the weekend.
He's too modest. He's also the interim football coach. That's right.
Howdy, y'all. I'm Chris Curran. I have the privilege of working with Jim and Stephanie and others in our engineering entrepreneurship program. I'm located over in 415 right here. I also run our engineering incubator. So anybody who wants to continue working on this idea or another idea, just come look me up right across the hall there, and happy to work with you and carry this thing on.
Good. Thanks. Okay, so while Professor Fred loads up the first presentation, Aggie MedTech, you can come on up. And so students, just a few logistics. There's a pretty good distance here to be from the judges. There is a table here if you choose to use it for your prototype. If you don't want to use it, then we can move it over to the side, but it's right here. You have the clicker on the table. Some of you practice with it, some of you not, but there's a nice big arrow that points, and then I think the top one is the pointer, should you want to reference that. You know you have 10 minutes. There will be a clock behind you. After the 10 minutes, you know there will be a 5-minute Q&A. I'll be sitting at the table behind the judges, and I will be the time moderator. The 10 minutes will be, the 10 minutes is a hard number, right? And the 5 minutes is a hard number, okay? Please wait just 1 second before you actually get started. Just kind of take a deep breath. You ready? The clock will start when you're ready.
Hi everybody, I'm Gavin. I'm Gerardo. I'm Unnat.
I'm Anna. I'm Riley. I'm Brittany. And we are
Aggie MedTech.
Fluoroscopy is used for life-saving procedures like implanting stents and catheters. However, it comes with a price. Fluoroscopy procedures release a larger amount of radiation than a normal X-ray. Radiation exposure occurs during every operation. This radiation accumulates over time in the body of our healthcare workers and increases the risk of cancer. Workers adhere to strict safety protocol, wear protective gear, and employ advanced technologies to reduce radiation exposure, but it's not enough. Doctors still have an exponentially higher chance of contracting brain cancer. These doctors and practitioners work very hard for the health and safety of their patients, but in doing so, they put themselves at risk. The preventative measures currently result in back pain and neck injuries, or are too costly to become widespread, and ultimately do not fix the problem, and even create more. Aggie MedTech was formed to ensure a safer working environment for doctors and staff. After hours of hard work and research, our highly skilled team developed Guardian Shield Ensemble. Guardian Shield was made with the focus on protecting our saviors from this radiation, while providing them a wide range of visibility, comfortability, and mobility when performing their procedures. Aggie MedTech, saving the lives of people who save lives.
So as we saw in the video, radiation exposure is a problem, and some current solutions for this problem include lead shield. This shield basically protects the whole body, but some radiation can come from the sides. And then the apron. This is great for the body and the core, but the arms and the head are exposed. Then the zero gravity device is basically great whenever it's blocking radiation, but the problem with this is that it's very expensive and it's also heavy, so it creates lower back injuries and multiple things. So then there's also the OSHA recommendations, but the doctor, they don't control how much time they take in a procedure, neither the distance from the source that is the patient. So are these current solutions enough? And the answer is no. So this brings us to our problem: radiation safety devices do not effectively protect health workers.
So our ideal solution would need to be lightweight. People need to move it around easily. So less than 205 pounds would be a 10% weight reduction from a normal shield. Accommodation is also a necessity for doctors of different heights and statures, ensuring proper placement within the device. Once they're in the device, doctors need to be able to deftly maneuver their arms to reach the patient and the equipment. So 120 degrees of arm movement should be required. We need to minimize radiation, so we need to decrease the amount of radiation reaching the doctor by 85 to 95%. However, for it to be feasible and widespread, it needs to be cost effective. So specifically like $1,500, which would be a 50% decrease from current solutions such as the lead shield. So keeping these requirements in mind, our first initial idea was the face guard, which would be a lead shield just mainly on the head, which would just specifically be focused on protecting against brain cancer. Our second was scintillators. So scintillators are a device that can convert X-ray radiation into visible light. So theoretically, they could be able to absorb the radiation before it reaches the doctor. The modified shield would be a full body coverage shield that would afford the doctor comfortability to move around.
So from these three, we chose the modified shield. We chose this because of its marketability compared to the face guard, where there's similar products already on the market.
It's realistic compared to the solicitors. Oh, my bad. Where that would need time to develop and research, and it's cost effective in that it's using technology that's already out there and kind of combining it, and it's functional by providing coverage for the head and the arms where that's the least covered for the doctors. And so this is our final design. In our original design, it was full gloves, while this one is more of a sleeve application with an elastic at the end where the doctors would be able to put through in gaps in the shield, and the shield would have a head region. It's effective material by it's materials we already know that are effective with stopping the radiation, and it's non-weight bearing compared to the lead aprons where it's on a structure instead of them having to go years and years of holding like 20 plus pounds lead. And most importantly, protects the head region where brain cancer is the
So let's just talk about the logistics of whatever materials we are using. So fluoroscopy machines operate at a range of 10 kilovolts peak voltage to 150 kilovolts peak voltage. So here we have a relation between radiation attenuation percentage and weight. So the energies which we have chosen are on the upper bound of the ranges of the fluoroscopy machine operations. So here we can see that the slope of these 2 points is the maximum, which indicates that there is the highest increase in radiation attenuation whilst being the lowest increase in the weight. So we can see that our optimal weight comes around 26 to 30 pounds. And since weight of the shield is directly proportional to the lead equivalency thickness, we have an estimate of around 0.8 to 1.2 millimeters of lead equivalency thickness, and that's why we chose with 1 mm. Also, the International Commission of Radiation Protection guides that the annual dosage limit for an operator on the body is to be 50 millisieverts, and for the eyes it should be 20 MSV, so as to avoid cataracts. So to account for these things, we have a radiation sensor inbuilt in our shield, which basically works on the scintillation detectors. It converts the radiation to a visible light, and then through an electric signal to a photodiode, and that measure would give us an estimate of how much radiation is being exposed to the doctor, and we can warn the doctor according to that if the radiation exposure exceeds the threshold. So this is our prototype. It's a scale model. It has 3 main components. It has the acrylic LED screen for the doctor to be able to see clearly through it. It also has the rag, which is LED fabric, to also protect the body of the doctor, but it has these special things, which are sleeves. The doctor can actually put the arms into the sleeves so that he can reach into the patient, like you see in the second image. And the third component it has is inside. It has a radiation sensor that would detect if the radiation passing through the shield is dangerous for the doctor, and it would signal him with the green light for safe or red light for not safe. This is a more realistic model if it were to be actually used in an operation environment. 2 main things that you should pay attention to is on the structure. There's a pedal underneath it. The pedal would help so that the doctor can either lower the screen or or raise the screen depending on the height of the doctor. Another thing is that the rag and the sleeve can attach or detach from the structure itself, because we understand that at some times they may need to operate quicker and they might need to take them away, but we do recommend when it's simpler procedures to always use everything.
And this is the items listed for the prototype to be made. So radiation sensor, a display, lead acrylic, wheels, hospital grade stainless steel, lead curtains, zippers, and a hydraulic pump. And with all that, the second column is the estimated item total for each item by itself, and the column all the way to the right is the total of what we would need to make an estimate to make the actual prototype. And on the last two bottom rows, the estimated total cost would be $1,100 to make. And we estimated to have a total of 200 pounds. Thank you. Any questions?
Judges.
Okay, nice job. I'd like to know what your thoughts are in terms of mobility for a doctor or somebody using the device. You talked about it moving up and down, but what about other kinds of movement the doctor would need to make?
Okay, so if you look at so the sleeves are actually they're really wide on the shoulders. I make them 25 centimeters radius, so it's really easy to insert the arms and also move around. The hold becomes tighter as they come to the wrist, so that it protects them, but it should provide them with enough ankle mobility so that they can really move around without too much obstruction.
And also it has a handle, so whenever the doctor is like moving around, you have that permission that you can just move around with you, the device. And the head, because of the sheet is in an angle, you can see the patient really well without like needing to move the device.
What about this kind of movement over the operating surface?
So actually here in the prototype you can see that there's an angle here. So it covers here, but it's easier for them to kneel down so that they can take a closer look at the patient.
Okay, thank you.
I have a question with respect to the sensor and how you decided on the location of that in your device with respect to the body parts that are of interest and maybe the location of the radiation source.
So based on I would assume this is a table we're operating, and I'm standing here. The X-ray spectrum would be coming from this. So this is the part where I would be most exposed to. So I would say that the placement of the sensor, we could place it around somewhere here and inside, so that we can see how much radiation is being exposed even after the lead acrylic sheet is preventing most of it. So that would account for most of the radiation and would give an overall better measure.
Did you give any consideration to having two sensors? One for like the head region and one for the torso? I think it was $45.
So based on our research, we were concluding on the point that this is the most exposed region. So that's why we only considered one radiation sensor in our model.
I have a question. It's a two-part question. First one, in your research, what is the most common cancer that you see typically in the surgeons who are using X-ray? What's the most common one? I know it's a very long chronic process, so it takes years for this to happen. And second part of that is cancer can be caused by many reasons. Fine. So how is it attributed by exposure to X-ray during surgery than something else? Did you see any data around that?
So I'm not sure on the spectrum of the cancers which are caused due to this, but we were mostly looking towards which is the most vulnerable region and what's the effective way to protect that area. So I would say that based on the densities of like muscles, tissues, bones we have in our body, bones have a higher density, so they would have better attenuation as compared to muscles or tissues. But we have not explored the spectrum of cancers which are caused due to the radiation.
Did you see any data which is attributed to this group of surgeons who have been using X-ray for a long time, and it is long-term longitudinal study of what kind of cancers they have typically?
exposed to?
So on the machine, on the fluoroscopy machine, there's a shield, and if it's not used effectively, the head can be easily exposed to ionizing radiation, which there is a correlation between doctors and brain tumors specifically. So brain cancer, which is really detrimental. So that's probably the biggest concern, which is why we kind of focus on the head region specifically, protecting that area.
Okay, Joseph, maybe one more.
I would just say in your rough cost estimates, is this you're looking? Looks like that's pretty fairly realistic. I mean, is there any benefit in perhaps going with more expensive radiation sensors versus more affordable ones in terms of accuracy, and how might that affect the effectiveness of your prototype?
So I made an estimated cost based off of common useful things that are made, because this is a prototype. From here we would actually advance it more if we had to. If we realize, hey, this sensor isn't working, maybe we need a more expensive sensor in this place. So this is just a rough estimated cost of easily common things to find.
Okay, great, thank you. Ray-Bans, you're up. So team, please take your prototype. If you would, just leave the clicker there on the table. Judges, as you finish your score, Sarah will be by to pick them up.
You ever had any surgery?
Team Ray-Bans, you guys just get up there, get settled in, but wait just a minute before we get started. We'll let the judges. Sarah. Yeah. Whenever you're ready.
You ever had any surgeries before? Yeah. So, who's got surgery on?
Do you know CPR?
Yeah.
Okay. I want you to take over chest compressions while Marcus operates the BBM, okay?
What's a BBM?
Stands for bag valve mask. It's used for when we
Typically have heart attacks. He's hoping young adults in their 30s will take heart health seriously.
Every day, a procedure is performed on the heart. Dr. Dietrich dedicated decades of his life to the field of medicine, saving lives, training thousands of physicians, and revolutionizing cardiovascular surgery. Dr. Dietrich died on February 23, 2017 of brain cancer, killed by the very techniques he helped pioneer. He was a living example of the impact of excessive radiation. In the spirit of this medical pioneer, we introduce a revolutionary solution: sensor cath. Equipped by the cutting-edge pressure and torque sensors, our catheters allow physicians to navigate with unparalleled precision at a safe distance from radiation exposure. The connected monitor becomes the eyes of the procedure, depicting real-time pressure data and providing an intricate view of the catheter's journey within the patient. Remarkably, positioning just 2 feet away from the exposure area reduces the risk of cancer by 80%. This breakthrough is not just a technological advance. It's a commitment to safeguarding those who dedicate their lives to safeguarding others, like Dr. Dietrich.
Good afternoon. We are Team Ray-Bans. My name is Kayla. This is V, Keyshawn, Arthi, Lakshay, and Zach. We are here to solve the issue that doctors are being exposed to over 6 times more radiation during fluoroscopic procedures than what has been deemed safe by EPA. And we are here to minimize that radiation exposure.
So what is fluoroscopy and catheterization? You need to know that to understand the procedure. Essentially, fluoroscopy is when a doctor is using a real-time X-ray to understand what is going on in the body. Additionally, a catheterization procedure is when the doctor is using just a catheter and a guide wire to navigate inside the body. This is not open heart surgery. This is the context in which we'll be explaining our solution to minimizing radiation.
When deciding on our prototype, we had 5 design requirements. We wanted to, 1, reduce the amount of radiation absorbed by the physician. 2, reduce the equipment weight to lighten the burden on the physician. 3, have a reasonable cost for the production. 4, increase the physician's mobility, allowing them to go through the procedure at a quicker rate and reduce the amount of radiation. And 5, have the prototype be universally used. By this, we mean that any physician would be able to pick it up and use it in their procedures.
With keeping these 5 design requirements in mind, we considered 3 solutions. The first solution is a protective exoskeleton, which not only shields from the radiation, but adds support and mobility. However, we chose not to pursue this path because we found the market for these type of devices to be already saturated. The second one is graphene, which is a lightweight alternative to lead protective coating. Since this material is relatively new, more research needs to be done before it can be implemented into medical devices. And lastly, our third idea was a redesigned catheter, which increases the distance between the source of radiation and the physician in order to reduce radiation exposure. Because of its functionality and low cost of manufacturing, this is the solution we chose to pursue. Therefore, introducing SensorCath.
Now with SensorCath, we are increasing the distance between the radiation dosage and the physician. We're taking advantage of the inverse square law, which I know math is very complicated, so I'm going to go through this pretty slowly. So the distance that you increase by, if you square that value, that's the amount of intensity that you're decreasing by. So for example, if you increase your distance by 2 feet, you're decreasing your dosage by 80%.
Like Zach mentioned, increasing the distance reduces radiation, which in turn also substantially cuts the need for protective material by about 50%. This lowers the weight that the physician needs to carry around day after day. Our product also fits seamlessly into the workflow of current catheterization procedures. They don't have to do anything differently. Additionally, our product has real-time and quantifiable feedback, which enhances catheterizations as they are.
Now, I'll demonstrate how our catheter works. Like normal catheters, you would have the sheath, which is inserted into the patient, and within it, the catheter would go through with its guide wire. The main difference is the length. This is a scaled down model, so with the actual prototype, we would have 2 to 3 excess feet. This end, the physician's end, is thicker because this allows them to distribute more force to push the catheter and guide wire in and into the patient. Now we have this hard exoskeleton, which is essentially just used to guide the actual catheter into a uniaxial path to go straight to the patient. Additionally, we also have a valve up in the front to allow to insert iodine dye or any type of saline solution. In addition, the main point of our catheter is that it includes a pressure sensor, which Arthi will talk about.
To understand why the pressure sensor is even incorporated, you need to understand how catheterization works. Now, there are 3 main motions that physicians use when using a catheter: push, pull, and twist. Additionally, they use the catheter to navigate using 2 methods. One is a fluoroscope, which is the main method, and they get some limited haptic feedback, which means when they push, they get a little bit of resistance, but even that is not massive feedback. The reason our catheter technology is revolutionary is because we're incorporating 2 things: a pressure sensor and a distance sensor. The pressure sensor will calculate the amount of pressure that you're getting back, resistance-wise, from the wall, and instead of relying on simple training or minimal haptic feedback, the physicians can now read the actual pressure number on the screen. That way, if they're pressing too much, they're facing an artery, something like that, they know exactly what's happening and they get a warning. Additionally, with the distance sensor, this allows them to calculate the size of something into place. Right now, stent sizes are calculated based on just looking at the image. This is based on years of training, it's based on how long of experience they've had in the field. This is not a precise science. So, with our sensor, by putting it in and out of the body, we have a wire distance measurement, which allows them to get a precise distance on what size the stent may be. This takes the guesswork out of catheterization. We are not simply minimizing radiation. We are also revolutionizing catheter technology.
Our estimated cost came out to be just over $300. Let that sink in. This is a really cheaper alternative to other options available in the market. And our product is also subdivided into reusable and disposable parts, which further decreases the cost because doctors and hospitals don't need to keep on spending on those components because they're already going to be reusable. Also, even though some parts are right now disposable, further research and development into this product can lead to them being reusable as well. Other benefits of our product are the fact that it's so quick and simple to manufacture and mass produce because of its modest design, and also that it's really easy to distribute because the infrastructure we need to distribute it is already in place.
We are gathered here today with one mission, to not only minimize the radiation exposure, but to also save the lives of those who save ours. So let us unite in making their well-being our collective priority. Thank you.
Judges, the floor is yours.
So Rob, you're the expert here, bud.
So you are talking about a clot that a physician is trying to reach and so we are talking two things. So when you are talking distance, so they are using the existing lead apron they use now. We are working farther from the table.
Right.
That's the concept, fine.
We want to decrease the amount of lead in the protection. The further they are, they need less lead protection. Ideally, we haven't done the exact numbers, but at least 50%, depending on how far away they are.
It's supposed to go from like currently 22 pounds, and we are aiming to reduce that to 10 pounds.
So I've just asked a question from an catheter is a very well established industry, fine. There are millions of them are used. So if I ask you from an intellectual property standpoint, what do you think would be a critical differentiation? Because you are designing a new catheter which has to be FDA approved. Is what would be that critical differentiation which you can potentially still protect as your IP?
It's definitely the combination between the sensor, because the sensor itself can be removed, but it's attached in a specific way to the outside catheter because the guide wire has to pass through it. So that combination is specific. And then we also have, as you mentioned, the thickness, right?
Yeah.
So you can talk about
The thickness is simply used to allow you to push the catheter that distance into the patient as well. So normally how the catheter and the guide wire length are, you would additionally just produce it with an excess length, with an excess thickness to compensate for that distance that it needs to travel.
Additionally, there was also a thing noted down where we were trying to measure the distance of the wire that goes in so that physicians don't have to guess looking at the fluoroscopy diagrams to see how much wire that goes in. And the patient can be relieved that the physician isn't just guessing some random number.
At the distance from the clot.
Yeah.
Yes.
I had a question considering maintaining sterility in your reusable device. How do you plan to either sterilize it between procedures and or prevent it from getting dirty within the procedure?
So we have a protective plastic coating, like this blue part right here. That's disposable. This is the only thing that touches the catheter or anything that goes inside the body. This is disposable, one-time use, and then other things are just sterilized the way that instruments are sterilized in ORs.
the sensor we chose are also specifically biodegradable ones. So we did not there's a specific name back there, but they have been rated to be used as biodegradable, they can be sterilized.
It's called piezo resistive miniature pressure sensor. I have a sample from FEDC which was similar to it, but it's not exactly the same.
So we chose materials that were already rated for this kind of thing.
I have a quick question and then a second. Quick question, I think, and hopefully that's a quick answer. You mentioned the size of the stent. Is that the length or diameter?
Length. Because we can measure how far the wire is going in. So that would allow us to measure how far they'll.
And is that an enhancement that you just thought would be an extra feature? Is it related to the radiation exposure issue that you're trying to solve?
It's
added feature.
Reduce time?
Efficiency, basically, of the physician performing the procedure.
Like, similarly, I was interested in the pressure sensor. You're trying to add enhance the feedback that you just manual have.
That'll aid in the safety as it allows the physician to not rely on the tactile feedback. Instead, they would have actual numbers to make sure they don't puncture any blood vessels.
And since the distance is longer that they need to cover, they get less feedback back without the sensor.
They already don't get a whole lot of feedback when they're next to the body. So when you move that 2 feet, you're getting even a little less. So we thought, okay, let's solve both issues by improving the sensor.
Now, I guess that was a related question, whether the feedback, the manual feedback be affected by the friction. I guess that's what you're trying to count, right?
Yeah. It also takes like years of training for physicians to have that muscle memory, and maybe with our pressure sensor, we're trying to solve that as well.
We're eliminating guesswork between the stent size. So instead of having to go back in and fix that later on if they mess up, you're doing it by just one procedure.
You guys expect any usability issues adding the length here, or maybe any torque issues or anything related to having to put more force on the catheter and the probe itself?
Yes, so that's why we made the back side of it a little thicker, so it's easier to maneuver since they need more force, since they have to cover that longer distance.
We wouldn't know this until we had an actual real prototype to actually have trial and error with, but theoretically speaking, since it's being constricted by the actual pipe, it should follow in a uniaxial path straight to the patient, and it should be used in the same exact way as normal catheters are.
And to also obtain some stability, the way we're tracking the distance that is going into the veins, it's a wheel that you can track the amount of rotation that it does, while it's also providing a stable direction for it to go.
Yeah. Thanks, team.
Thank you.
All right, team RDS, you're up. Clicker left on the table.
That's back. It's a wonderful day.
Samantha, the clicker's back on the podium somewhere, so just so y'all be ready. Wait, let's give the judges just a minute to finish.
Ready? Got it, everybody.
Meet Dr. Larry. Dr. Larry is a cardiologist who uses fluoroscopy. He has a wife and 6 kids at home. They're proud of his work and rest easy knowing that he uses typical radiation safety gear. But they don't understand the risks. Physicians like Dr. Larry have an 800% higher chance of contracting brain cancer than the general population. Standard fluoroscopy PPE protects the torso, groin, throat, and eyes. However, the current solutions for the head are cumbersome and expensive, and therefore are often unused. Other than radiation-resistant glasses, the face goes unprotected, increasing the risk of brain cancer 8-fold. 85% of these tumors occur on the same side as the C-arm. By the year 2030, the market for surgery involving fluoroscopy is projected to double. Unless novel solutions for radiation protection are found, more physicians like Dr. Larry will face a disproportionate risk of preventable brain cancer. Our team worked tirelessly to solve this problem and discovered the Nemean. Based on the Greek legend in which Hercules kills the Nemean lion and wears its head for protection, we created a surgical hood with unparalleled radiation protection. The Nemean is made of a polymer shell and hydrogel filling with lead oxide suspended throughout. Innovative and transformative, the Nemean heralds a new era in radiation protection.
Well, thank you for your attention. My name is Mary Grace. This is Henry, Aiden, AK, and Sam. We are Team RDS, here to present our product, the Nemean.
According to the NIH, 0.25 doctors are exposed to 0.25 milligram of radiation per scan directly to the face. So whenever they're performing 10 procedures a day, that can add up to 2.5 milligray of radiation directly going to their face. So radiation damage accumulates over time with low exposure. So that means that per 1 gray of radiation, your chance for cancer increases by 10%. That means that over a lifetime of practicing as a doctor using the fluoroscopy machines, your increased rate of cancer could be 800%.
So we've identified 5 design requirements that we believe need to be met to meet our consumers' needs. First, we want at least a 50% price reduction as compared to Biotronic zero-gravity lead system. This system is upwards of $100,000 right now, and as such, many hospitals aren't providing this system, and it's not really available. So with this price reduction, what we're hoping to do is increase the availability of these safety systems for our physicians. Secondly, we want at least a 30% increase in coverage over the head. Current lead caps that are the industry standard that is typically worn in these procedures only cover about 27% of the head, but leave the face, the temporal regions of the skull, and under the chin completely exposed to this harmful radiation. So by increasing this coverage, we hope to make our physicians safer. Thirdly, we want to minimize the size, as the OR is already filled with many people and many large machines, so we don't want to add something that's going to obstruct their mobility or get in the way and potentially cause more complications to arise. Fourth, we want 20% less weight compared to the standard lead cap, as many physicians who do these procedures have reported higher instances of neck and back pain, which we obviously want to reduce. We want to reduce these rates by decreasing the weight being placed on their heads. And finally, we want no additional training required or installation time, because these physicians are very busy. We don't want them to be dissuaded from using one of these safety products because they have to find time to get trained or have it installed in these hospitals.
So based on our design requirements, we invented 3 solutions. And the first one that we invented here on this side is a lead-infused dome capsule that would actually attach to the C-arm. And whenever the C-arm is being used, the dome capsule would extend and encapsulate the entire patient. This would protect the entire OR from radiation. The second solution that we invented was the polymeric lead-infused curtains. And although this isn't shown in our photo, what's unique about this design is that these curtains would actually hang from the top of the C-arm itself. And whenever the imaging was happening from the C-arm, the curtains would drape down over the patient bed, protecting the entire OR from radiation. And once imaging was done, the curtains would be rolled back up. And the final design that we invented is the Nemium, which is a radiation-resistant helmet that the surgeon can install or can put on before surgery begins and wear throughout the entire operation procedure. So we made a simplified Pew matrix to determine which of these designs was best, and the Nemium was the clear winner. One of the major problems that we wanted our design to solve was the issue of convenience of using our device in the OR. While the leaded capsule and the polymeric curtain would both effectively shield against radiation, both of these designs required additional steps for implementation and uninstallation every single time imaging was done. The Nemium, on the other hand, would simply be put on before surgery began and worn throughout the entire procedure, so it would add no additional inconvenience.
The Nemium, it's wearable, it's lightweight, it's affordable, and it's practical. The Nemium, the top includes a polymer for rigidity, and it's going to be held off of the face using a cushion on the forehead and 2 clips, one on each side, that can clip to the surgeon's radiation safety goggles, so they can bring their own. If they've got their specs on, or if they have the lights, they can bring their own stuff. They can use it with our hood. The bottom doesn't have the polymer. It'll be more flexible, so it can be tucked into the neck of the surgical gown, maintaining a sterile environment in the OR, and it's out of the way, but it's still protecting the bottom of your head and your neck from radiation, because we don't want that radiation getting behind the helmet and then bouncing around on your face. That would be bad. The back of the Nemium is adjustable inside and open to ensure that the Nemium is not only comfortable and practical, but accessible. Any surgeon from any specialty, whoever is in a room with an X-ray machine, can and should be wearing the Nemium.
So the materials for the Nemian, after extensive research on affordable and lightweight materials that are known to be that have radiation shielding properties, we've identified a few. Each one of these materials we've decided to infuse with lead oxide, which is an industry standard for leaded glass to prevent radiation from getting to individuals. It's typically done in ranges of 20 to 30% by weight in this glass. So for each of these layers, we decided on a 30% lead oxide by weight in each of these layers to prevent radiation from getting to our physicians. So the very center of the Nemian is a hydrogel suspension with lead oxide particles suspended in this. The reason we chose a hydrogel was for the high water content that it has, because water is known to have radiation resistant properties, and then in combination with these lead particles, we believe that this will only fortify the radiation resistance that we can provide to our physicians. Surrounding the hydrogel is a lead oxide infused HD polyethylene, high density polyethylene bilayer. What this does, polyethylene is a known radiation resistant substance. It's actually been used on spacecrafts, and it's readily available and cheap. It's actually used to make milk jugs. So it's very available. And then when we fortify this again with lead oxide, we believe that we can maximize the benefits that we're achieving, or that we can get from this material. Finally, surrounding both the polyethylene and the hydrogel is a lead oxide infused vinyl capsule. The point of this capsule is to form an airtight barrier around, so that way the hydrogel doesn't dry out, and we can contain the water within this, so that we don't lose those water radiation resistant properties. And again, the entire Nemian is surrounded in polyester, so that way it just provides comfort towards our physicians and can be easily cleaned.
So although there are current solutions that protect the head from radiation, like the zero gravity from Biotronic, they're exorbitantly expensive and they are not available to your average physician. So our goal in making the Nemian was to target accessibility, make an accessible protection for the head of these physicians. The typical PPE that these physicians would have includes the face shield and the lead cap. So when you are doing fluoroscopy with the C-arm in front of you, the radiation comes from below and in front, like in the diagram in between the face shield and lead cap. Now the lead cap offers very little protection from this radiation. It covers about 27% of the area that it needs to be covering. The face shield is a lot better in this regard, but it still leaves major gaps around the jaw and the face, and it also does not cover the sides of the head. And actually, the temporal region of the brain is where the majority of the glioblastomas that are showing up in these physicians' heads are. So the side is very important. The Nemian, on the other hand, as you can see, provides complete protection from all sides for the head of the physician. Additionally, it is 1.4 pounds, making it significantly lighter than the lead cap at 2 pounds. And the manufacturing cost is going to be roughly $17.50, so this could be very accessible for surgeons. So we talked to 4 surgeons who have worked with fluoroscopy, and we told them about our solution, and they had very positive reviews. Some of them even saying that if this were to exist, they would definitely use it in their own practice.
Thank you. Do we have questions?
Judges? Sure, I'll go. Love the interviews. Way to do that. What's your intuition about comfort, breathability, heat buildup, and other kinds of sort of wearability issues?
Sure. So it's open in the back, and I have actually spent a lot of time wearing it this weekend. This is the real materials, obviously. It's open in the back, so the early models will have breathability, but we actually wanted to have a future work slide, but decided, and for the sake of time, we could talk about it in our questions. We potentially would be introducing an AC unit in the same way that the orthopedic surgeons have the AC units in their helmets when they're wearing the full hazmat suits. That was actually feedback from one of our customer interviews. So a later iteration of the design would potentially include AC to make sure everybody is cool and comfortable. But as of right now, you can wear it for a couple hours. I promise I did.
So your key innovation here is the material point.
Yes,
That's the key innovation. Hydrogel is being used in other radiation protection. I know about lungs for swallowing and all those kind of radiation therapies. So this lead oxide infused hydrogel, is it an existing FDA approved material, or this is where you guys hope that this is going to protect radiation effect?
So I'm not aware if it's FDA approved or not, but we did find studies that are papers that published on infusing this hydroalonic acid hydrogels with lead oxide, and it was shown to prevent radiation from going in there. Ideally, like the FDA wouldn't have. I mean, it's not. We don't know if it's FDA approved, but since it's contained inside the nemean and it's not, it has multiple layers in between this. Ideally, it wouldn't come into contact with the person, so toxicity shouldn't be a risk, and it's able to merge with the hydrogel.
And did you see, just a follow-up question on that one, Dan, did you see in your studies that when they're using this, presently the plugs are very tiny, because they use for the hydrogel, but you're talking covering a much larger surface area using a material like this. And did you see any more details about the thickness, refractory effect, and all these kind of things of having something like that?
Yeah, so the thickness that was showing up in the papers and what we had saw with the lead, ideally the hydrogel center of this would be about 0.5 centimeter. It's a little bit large, but because of how lightweight all these materials are and how flexible the device is, to be able to fit into the garments that the surgeons or cardiologists are wearing, this shouldn't pose too much of an issue. But of course, we'd have to do more testing and see how that all comes together.
What about eye protection? Is that just
So that is something that surgeons bring on their own, because we wanted to leave it open because, at least from what I've seen, surgeons like having their specs and their lights and all of their fancy gadgets on their own goggles. So we wanted at least the option that it clips to the surgeon's goggles on the inside, and they can bring their own radiation safety goggles, which they would be wearing in a room with an X-ray machine.
My question was also about the material, but that was answered when you was asked.
Time for one more if anybody has one.
Quick question, any other FDA approved product like this? So you guys, I think, know 510K and all at this point. Any other product which is approved with hydrogel for radiation safety?
We've only seen the smaller plugs, like you mentioned. I've also seen the polymer has also been extensive studies on radiation attenuation when you infuse the polymer with the lead oxide. So all of the materials we're suggesting have been tested and shown to work. None of them at this, all of them at this scale, but none of them in something like this, which is why we're here.
The lead polymer was actually used in nuclear waste testing instead of medical, so it was really tested extremely. So.
Good. Nice job. On the table there. There we go. So we won't confuse the next team like you were confused. It's an honest mistake. They weren't trying to. Good job. Okay, 6 cents.
Right.
Just 1 minute before you get started, let's let the judges have a moment.
So play the video. Hold that. Actually, I was so rushed. You want to hold your glasses?
Okay, 6 cents whenever you're ready.
basically, the problem with radiation is that it's a double-sided sword, right? On one hand, you have the patient who gets really good benefits from this service, whereas the physician experiences the worst end of the deal, right? He gets the radiation over long periods of time. The exposure is bad, it causes cancer. So there's a need to reduce irradiation for the fluoroscopy physicians without sacrificing the benefits to the patients.
Alright, so when we made our product, we had 5 design requirements. The first one was to mitigate irradiation, and so according to a study that was done, if a doctor is exposed to more than 50 millisieverts of radiation annually to the body and 20 millisieverts annually to the eyes, they have an increased risk of cancer. So we're going to try and make it so that they're exposed to less than that annually. Second was usability. We want to target what the hospitals would want. The hospitals want it to be easy to maintain, easy to sterilize, and also last long. And so some things we thought about too with usability. Next was adaptability. Hospitals are different. A lot of fluoroscopy rooms are different too. We want to make sure that our product can be used in many different rooms with many different operations. Some operations have 1 person, some have 3. We need our product to be able to use in different environments and protect them from those environments. Next was mobility. In no way can our product inhibit the use of an operation that's going on. Our product can't make it harder for the doctor to operate what's going on. That would require training if we had a big thing, or it would require a lot of changes, and we can't do that. It would defeat the purpose of the operation. Second was cost effective. We want our product to be less than that of the current market solutions.
We looked into 3 possible designs to satisfy these issues. First of all, we looked into a automated shield, which was a protective barrier lined with a material that would reflect radiation, therefore reducing the risk to the doctor. The second prospective design was a melanin-lined mask. This is a special type of melanin derived from fungi that would absorb the radiation, therefore reducing the exposure to the doctor. And the third design that we looked into was a sensor attachment to the surgical eyepieces. This would detect the radiation exposure doctors would receive during operations and inform them of their risk.
So based on these, we decided to make a decision matrix or a poop matrix. We took all 5 of our design constraints, we rated them on a scale of 1 to 5, and applied these constraints to all 3 of our designs. The sensor attachment passed by flying colors. I mean, 14 to 3 to 0, right? So let's talk about why it's such a great device.
Alright, so what our solution basically is that we realized by a study done by UC San Diego is that the equipment that's already in the hospitals, the radiation shield, the suspended one, it can protect against 90 to 98% of the radiation. So our solution shouldn't be to create a whole new big thing. It should be to make the shield more effective. And the problem we saw was that doctors often, more often than not, either don't know how to use the shield or forget to use the shield. And so oftentimes the shield is capable of protecting them. They just forget to use it sometimes. And so we want to make a device that could scan the radiation that's hitting someone and warn the doctor of that radiation to remind them to just move the shield. That way, and so we had 4 components, and we're going to go more into those on the next slide.
So essentially the key features of these components, the main one being the dosimeter, which essentially takes in the measurements of the intensity from the x-rays. It produces a record of it, and you get the visuals around the cranium, essentially. And then you can take these readings and apply an LED warning system from a code. Basically, an LED will light up to notify the physician that he's experiencing high doses of radiation. The software, we'll talk about that in the next slide, but essentially we'll have some threshold values on some values from the X-ray radiation.
So this is our final 3D CAD design. One interesting thing about our design is very adaptable. As you can see here, we have a simple clip that could detach and attach the device to the optical lenses, which makes it very adaptable for various types of eyepieces. Secondly, it's very easy to use. It's just a simple clip. Thirdly, we intend to eventually have a USB port so that you could record data collected during operations so that you can have long-term data about your exposure during the period in the operating room. Fourthly, it's a non-invasive, therefore it's not going to interfere with regular operations. And lastly, it's a Class 2 medical device, therefore it's going to eventually get into market.
Alright, so this is the real power of Sixth Sense. The first one is it's cost effective, right? Unlike a lot of other solutions out there that require you to build a whole new structure or machine, this one is utilizing what the hospitals already have. It'll be easier, it'll be very cost effective, and it's proven equipment that's proven to work, right? Second thing was that it's simple. We actually tested the goggles on some people. Some people even said, like, if you wear it for more than an hour, you'll probably forget it's even there. We made sure it was balanced on both sides and it's easy to clip on and it doesn't touch your skin in any way. Right? Second thing was safety. The goggles will have an equipped USB, and the USB will be able to transfer data to a computer, so we'll be able to log long-term radiation experiment or exposure on doctors over time, so they can see their risk of cancer over like long periods of time, depending on like how many operations they've been through. Same thing was real-time training. Now, if doctors are trained with this equipment that can tell them when they're being exposed to a lot of radiation and about how much they're being exposed to, over time they'll be able to like really understand where to move the shield more effectively. It'll become like second nature to them, right? And it's really helpful, and those are the real advantages of 6 Sense.
So this slide shows the inverse power law that is associated with radiation. With the software, we want to implement a soft threshold and a hard threshold. This is really at the leisure of the doctor based on his preferences. For the soft threshold, it'll be around 1,000 microsieverts. It'll implement a timer at the doctor's discretion. So when that timer expires, the LED will come on and notify him to change, make an adjustment somewhere. The hard threshold is where it doesn't matter. You need to get out of there. You probably need to make an adjustment. It's too high. So that's how we got all of those values from that graph right there. So all of our solutions are already pre-integrated. Really, the big one is just adjusting the lead plexiglass shielding. This gives you that intuition to move it around. Why spend $4,000, $5,000, $6,000 on a device that you can't use to its full efficiency, right? The second one, we can strategize X-ray on and off patterns. This saves power as much as it does saves the physician from overly experiencing X-ray radiation. Number 3, we can reduce X-ray image frame rate. This lowers the power as well, saving cost, while also saving it from excess radiation. Or we can incorporate more distance from the source. This is at the leisure of the doctor once again, but it depends on the procedure. And also we can alter the X-ray orientation, once again, depending on how the doctor is performing the operation. So all of these are meant to optimize how the devices that already exist, and you want your best bang for buck, right? So this is how we do it, and we reduce the overall power cost as well. So our market is, this is our market strategy. The target market is medical industry and fluoroscopy physicians. The first year, we want to finalize our research, move on to exploring device variations and prototyping. In the next year, we want to start applying for the IDE application. By year 5, we think that would be a good bookmark for that, and that will lead over to a pathway to clinical trials, which quick, easy path to 510K approval. So we're expecting a projected cost per unit of about $100 to $200 per unit. It's really cheap, so we expect this device to really take over the market. So thank you. We'll open the floor to any questions if you have any. I have a question. As you're talking about using it to reposition the shield, is there any way it gives the doctor some sort of intuition as to where to move the shield, how to move the shield?
We did have some discussions on that, and we were kind of hoping that would be a question, so thank you for your question. Basically, if we were to implement multiple sensors, right, you could get a lesser value in this one on radiation. Like, let's say you have a quantity that's smaller than this side, you would know to move it towards the higher side, right? So you can build a directional intuition on that. And also you can implement a sensor lower, right, if you want to protect against the core of the body. So there's a lot of options and avenues for our device, and yeah.
You use the magic word 510K and class 2 device, so assuming you know that space, what's a predicate device for this?
Well, we do know that there are stickers they use in that operational room, like they're color changing based on the radiation levels of that room, or I heard there's a popping one as well. So I think those are the really predicate devices. There are sensors that do exist that detect X-rays, but I haven't seen anything being implemented on the physician itself. So right now it seems like a really open market. So,
what about the weight and the comfort with the device?
Yeah, I mean, if you want to try it on, feel free. You're good? Okay, well, I mean, I've tried it on. It's pretty comfortable. It's not that heavy. The system itself is
does it worth? How much does it
we haven't weighted. That's just a prototype. Right. That would depend on how much the sensor is itself. So right now, it's hard to say right now.
On Fusion, the calculated weight is like 2.2 something else. Right, that's assuming the sensor weighs like a little bit more.
What do you think the incentive is going to be for the doctor to purchase
What are these?
Well, it gives them a knowledge on the background of radiation he's been exposed to, right? So there is a hard limit regulation. It's about 50 receivers per year, right, annually on the body and 20 on the head. So with that knowledge, he can better implement his shield, but also he can understand like his risks, where he can take time off if he feels like he needs that. So it's up to the doctor. It gives him a lot of freedom in his own operation room, which is what we're kind of going for. We want to be like close with the doctor, close with our customers. So that's the goal.
Also, the company which the doctor is employed by, they'd be very interested with this data because that gives them a decent idea about how exposed their doctors are, and that gives them a better indication oh, this doctor might need to sit out for a few months because of being overexposed to something.
So my one question here is, these companies are making like Siemens, Philips make these devices. They know this problem. So what kind of efforts do you understand they are trying to make from a source standpoint to prevent this or try to mitigate this issue? Like, is it something you would want to work with them, considering you are going to have a lot of this information on the radiation source?
Absolutely. I would love to work with a company that has already knowledge in this field, so I'm open to that for sure.
Maybe one more if anybody has one.
So the velocity is the monitoring of the warning, right? And you mentioned some different warning categories. Is that based on this cumulative exposure?
Yes, so it'll basically download all the information into like an Excel file, into a little box where the battery system and all that. So, I mean, that information, I want to do it by every 5 seconds. There's a measurement taken, and if there's like a timer, right, during the soft threshold. So during that time, if all those numbers are above that value, then it's going to implement that warning. And we're still playing around, it's just a prototype, so there's a lot of different options. Yeah, does that answer your question?
All right, thank you. Go back. So if you would just move the little black table to the side somewhere and put it back when you're finished.
Yes.
Like your mother would tell you to. It's very important.
Yes. Yeah.
At that moment, it struck me that I will never be that cardiovascular surgeon again that I was. The last thing I was thinking about was how much radiation am I exposing my body to? Being a doctor, my whole motive was to help the patient and get the patient well. I didn't think about the hazardous conditions.
Fluoroscopy procedures on average yield 3,000 times more radiation than a simple limb x-ray due to the need for real-time images. Physicians use lead shield aprons to block the radiation waves, but they aren't always effective. COMX tackles this problem. Instead of physicians wearing the shield apron, a lead blanket would be suspended over the patient that blocks scattered radiation from reaching the physician. This design provides easy vascular access and avoids patient compression. And that's not all we changed. At ChromeX, we changed lead at a micro-scale level, reinventing X-ray shielding. Its novel cone-like geometry reduces lead mass without compromising radiation protection. ChromeX innovates radiation protection, saving the lives of those who save ours.
Sadly, Dr. Edwards did not make it. He was taken out at the peak of his career due to radiation exposure. We are COMEX. My name is Ola Hamdi.
I'm Rishi Panjwala. Howdy, I'm Manish Simnigunta. I'm Ankit Kumar.
And I'm Bharat Kaur.
So the problem that our team discovered was there is inadequate protection for healthcare professionals, and this is increasing
radiation exposure to medical professionals. This is also evidenced by an 8x increase in the risk of brain cancer for healthcare professionals when comparing it to regular people. So there are already a number of protection devices for exposure to radiation on the market. So the first one being the lead vest. But each one of these have a weakness. So the lead vest, it covers the majority of the body, but you don't have protection in either the extremities or the face. The same problem is present with the lead-lined goggles. You protect the eyes, but you are ultimately lacking protection for the brain. The third one is the lead-lined shield. So this provides the most amount of protection, but it reduces the accessibility and mobility of the physician while they're doing a procedure.
With that in mind, we've come up with 5 design requirements. The first of which is its durability and reusability. We would like something that physicians can reuse and wouldn't be a one-time use compared to a lot of the things in the medical industry. And with the ultimate goal that it reduces radiation scattering. We also want it to be accessible. We don't want this to be something that only 10% of physicians can employ. We want this to be found everywhere, from tertiary hospitals to heart institutes. With this comes an ease to use. Easy to use means that it's easy to incorporate and implement in current workflows and procedures. We want this to be not as cumbersome, least cumbersome as possible. And with that, we'd also like to focus on a time to market frame, timeline, in that we want something that can come relatively quickly. We don't want something that's going to be stuck in research and development for a long time, as many products do. With that, we came with 3 possible solutions: COMEX, AI upscaling, and an X-ray containment box. The problems that we found with AI upscaling were that it wasn't as applicable as we thought. Human vasculature varies differently from patient to patient, and it wasn't as easy to use as we imagined, as not everyone is as tech savvy. One other thing we thought about was the X-ray containment box, and our implementation did not actually reduce X-ray scattering in the way we imagined. So finally, we chose COMEX.
So COMEX is a revolutionary piece of technology which introduces innovation at 2 different scales. So we have an innovation at the micro scale, which manipulates how radiation is being absorbed by the lead, and then we have a manipulation and an innovation at the scale of an entire patient. So let's look at the manipulation at the scale of micropattern in the first place. So on your left-hand side, you have a plain old boring piece of lead, which is used right now in the aprons worn by the doctors. On the right-hand side, you have this comb micropattern, which is essentially grooves that are embedded on the surface of lead. What happens is that when you have X-ray, it hits the lead block. Some of it is being absorbed, some of it passes through. But when you have this micropattern, because of the change in refractive index, it allows X-ray to bounce on the surface, increasing number of interaction events between lead and X-ray, thereby increasing its effectiveness in absorbing the radiation. We did this test. So we are passing a piece. We made a small prototype. So this prototype is made out of acrylic. We had a flat piece, and then we had a piece with honeycomb-like patterns in it. And then we tried to pass light through it. What we found was that on the left-hand side, if you have a flat piece of sheet, most of the radiation goes through. But when you have this piece with this honeycomb pattern on it, it's an exploded form of the micropattern. Wherever you see the black dot, the radiation is being absorbed. And these are the same spots where you have this pattern, which shows us that the hypothesis can work. The main utility of this pattern is that because you have this pattern on the surface, you're removing some lead from the surface. And because you're removing lead, you can reduce the weight by at least 25%. Also, we are increasing the surface area present on the top of the surface, thereby increasing number of X-ray interactions and more absorption. And then these 2 pieces of technology come together to create 30% more effective shielding for the clinicians.
Which brings us to our second component of COMEX. The second component is a lead blanket. This lead blanket is going to be suspended right above the patient, held together by clamps on either side of the bed. So this blanket would have various access points to prevent the physician from feeling any limitation to their accessibility or mobility. So these access points, we did some research on typical fluoroscopy procedures, These access points are most commonly what are used in catheterization. So we have the femoral artery, you have an access for each femoral artery, both radial arteries. And then we also have multiple sized patches on the chest, because there's no need for us to expose more of the patient's skin, more of the room to radiation than necessary. So there's sometimes when procedures use a smaller X-ray compared to other procedures. So to reduce the overall radiation, we decided to have multiple sizes. Additionally, since the blanket is suspended right above the patient at the source of the radiation scatter. Because when you look at fluoroscopy procedures, the X-ray comes from the bottom, and the radiation scatters right when it hits the patient's bone. So, by having the blanket that's suspended right above the patient, the radiation is contained at the source, which means there's going to be less radiation throughout the entire room. So, physicians would have to wear less shielding. Currently, physicians wear about 22 pounds of shielding on their body, and let's say they do fluoroscopy procedures all day, that is exhausting. That's going to cause so much back pain, so much neck pain, and we really want to eliminate, or we want to decrease that as much as possible. So by containing the radiation at the source, we can decrease the amount of shielding because there's not as much radiation flowing through the rest of the room. Additionally, because it's just clamped on either side of the bed, it's really easy to implement, it's easy to deploy throughout various hospital systems, because we're just clamping it on either side, and it's going to hover right over the patient. It's pretty simple.
Not only that, but COMEX appeals to multiple people. It's not only used in hospitals and imaging centers, but it could be used in nuclear engineering labs, as they are also exposed to continuous radiation. Besides that, it could also be used in the space industry, as they also deal with radiation and have a weight problem, and that is something that we tackle. Here at COMEX, we innovated radiation protection using our cone-like technology into the patient-leaded blanket. We are saving the lives that save us.
Judge.
So you're talking about designing, it's just a new design of the material that could be used for both as a blanket or even the apron.
Yeah, it's an additional application.
So it's just not, so kind of completely redesigning how this thing works. So going back to your material design, so you are really talking the same existing material like lead, but able to create these micro patterns in that, and try to come up with these designs of blanket or apron. Do you know which are the biggest manufacturers of these lead blankets? Which companies do these products or bring to market? Is it the same Philips, Siemens make these fluoroscopy, or there are other companies who do that?
I think it's mostly other companies who make that, but Philips, usually companies like Philips or GE buy these blankets from these companies, and then they sell to their customers. So I think it's mostly like smaller scale companies, and the bigger companies buy the blankets from them.
Do you have any sense of what kind of, you showed a data passing a light, this refraction, any sense or percentage, some quantifiable number, like what's the reduction in the radiation that can this device can?
So every time X-ray bounces once, you have an interaction event because it's bounced, right? So with successive bounces, you have multiplication of the number of interaction events, and the absorption grows exponentially.
Is there any sort of similar material that's been tested in research, and is there any data available on a similar type pattern?
Data exists for metal-shaped microcomb patterns, and the data doesn't exist for X-rays in particular. It exists for other kinds of electromagnetic radiation because the comb pattern has been shown to absorb other electromagnetic radiation really well. So we thought that it would also work for X-rays if you put this pattern in the lead.
They have a similar wavelength.
Similar wavelength.
That was my other concern. Is X-rays are extremely short wavelength, and that's in some of the research I've seen. Is the issue is it relies on atomic nuclei size to block it because it just passes right through the atoms.
You're exactly right, and that's why we did not ignore the nuclei size. That's why we still kept lead in place. We just changed its shape.
Related to those questions, the slide that had the percent reduction with the percentage. I think it's at 30%. I think it's at 30%.
Yeah, that's what he estimated.
can see how the first two would be easily calculated. How do you calculate that third one?
So we estimated that this would be somewhere in between the first two, because to estimate how many number of interactions are happening, you will actually have to create a simulation model of it. And the deeper your grooves are on these patterns, the more number of interactions would happen. So you would have to consider the manufacturing challenge of how deep these grooves can be made to increase that effectiveness. So we kept the simplest possible number we could keep for groove, which is about, I would say, micron or 2 micron point.
Is there precedence for coverings, drapes, or some other kinds of materials suspended over the operating table?
As far as we can tell, there's nothing that's suspended over, but there is like a predicate device for a lead blanket. Currently in like dental x-rays, like when you go to the dentist and get an x-ray, you wear like a radiation blanket, they just put a blanket right on top of you. But we found that kind of design can be like really compressive for the patient, especially since we don't know how long, like these procedures can range from like various times, right? So we wanted to suspend it so we can still have it as close to the source of the radiation scatter as possible, but it's still not going to compress the patient. Even if they can't feel it under anesthesia, might as well be safe than sorry.
Again, I will go back to FDA because that's your primary initial barrier. What other applications they have used? You said a lot of very good applications, nuclear industry and space. Do they have any other products now in space they're using which have similar form factor, like micro pattern, fabrics or coatings or anything like that at this point? Like other industries, not healthcare.
My guess would be that they would be using it, but it would probably not be out there since it's protected technology. So it was difficult for us to find out. We tried, but we couldn't find it.
I would encourage you, if you don't find it, you should file for a provisional patent. At least in US, you can do that.
Okay, thank you, judges. So the clicker, would you put the clicker back on this table? So Team Z, you're coming up, and as Team Z is coming up and getting ready, and the judges are finishing up the marking for this last group, let me talk a little bit about logistics. When Team Z is finished and the judges are finished with their grading, the judges and a few of us will go to the room next door for deliberations. Students, you will stay, participants this weekend, you will stay in here. There's a survey for you to fill out, so there'll be a QR code for you to load up on your phone and answer some questions for us. Once you're finished with that, then at Ms. Amaya's direction, you're going to go out for a photo. I think down on the far end of 400, there's the A&M logo there, and you're going to go there and take some pictures. Once the judges are finished with our deliberations, we'll actually join you. So once you're down there, you'll just stay there for a few minutes. We'll take care of all the looking beautiful and taking photos things, capturing the event. Then we'll come back in here for awards. Okay? All good? But don't leave here. Once you're finished here, you're logging onto the QR code. If you don't log on the QR code, no award for your team. Just saying. All right. Team Z, you're up.
Every day, medical health professionals save lives using fluoroscopy, a technique in which X-ray is used to visualize a patient's vessels in real time. Fluoroscopy is used to treat patients suffering from heart attacks, strokes, and other arterial and vascular problems. While professionals are hard at work saving lives, they are vulnerable to extreme doses of radiation for hours upon hours every day. Most commonly, leaded vests, skirts, and goggles are used to protect the torso, legs, and eyes, but X-rays penetrate the skull through the professional's exposed face. Consequently, a significant proportion of medical professionals suffer from brain cancer, the cause of which has been linked to the scattering, ionizing X-rays emitted from C-arm fluoroscopy machines. Every time a doctor is exposed to radiation, it irreversibly increases the risk of developing cancer. While there are systems and methods in industry that address this issue, they suffer from various setbacks and hurdles: high cost, limited availability, and long-term health issues for the medical professionals from the burden of wearing 20 plus pounds of lead clothing for hours at a time. As a group of young engineers looking to make a difference in the world, we have stepped up to take on this issue because we must save the lives of the medical professionals that save ours.
Howdy, we're Team Z. My name's Cade. I'm Christos.
I'm Caitlin.
I'm Maddie.
I'm Sam. And I'm Sophia.
And this is our radiation and healthcare presentation.
So let's keep this short and clear. Medical professionals are exposed to tons of radiation every time they perform fluoroscopy. Not just doctors, but also nurses, technicians, anesthesiologists, and everyone else who's in the room. And while protective methods exist, they primarily focus on the physician. They're heavy, expensive. So when they're performing this procedure and they're exposed to up to 3,000 times more radiation than a simple X-ray, they're put at 8 times more likely to develop brain cancer.
Current methods. So I'm going to talk about the current technologies that we use to prevent this problem. First off, radioprotective barriers and clothes. So we have vests, we have a shield for thyroid, and we have a lead cap. The problem with this is, first of all, it does not protect the face for the most part, and second of all, it can range from 15 to 22 pounds. Physicians are not 20 years old. They can be 40 to 70 to 80 years old, and this will cause detrimental effects in the long run. 2, hardware and software optimization. The physician during these procedures is looking at a big screen which has a frame rate since it's a live image. These frames can range from 15 to 10 to 4 to 2 to 1 frame a second that directly correlates with how much radiation is being emitted from the machine. This is optimized by the physician without compromising patient success, procedure success. More advanced systems do exist, like the more advanced suits that are being used, but they are very heavy and very expensive, being inaccessible to most hospitals. Lastly, we have radiation quantification, which comes in the form of dosimetry sensors. They can be in badges, integrated into the lead vest, or independent. They are great at quantifying radiation on each person in the room, which is very important. But the issue with this is that we have no standardized methods of correctly using this information to fix the issue.
These are the 5 design requirements that we came up with. First and foremost, we want to reduce the radiation that is affecting each healthcare professional in the room. We don't want to interfere with the procedure. We want access to all the critical points that are necessary to the procedure. We want to make sure that our device can be used in time-sensitive situations, such as when a patient is having a stroke or a heart attack. We want our costs to be reasonable and accessible for most hospitals, and we want to minimize the weight effect on physicians' bodies, or not add to it at least.
Based on these design requirements, our team came down to 3 potential solutions. Our first solution option was to use alternative imaging techniques such as MRIs and ultrasounds in combination with fluoroscopies to reduce the amount of time that a medical professional would be exposed to that fluoroscopic radiation. Our second proposal was to use an array of modular blinds around an imaging site to prevent X-rays from deflecting towards medical professionals. Our third proposed option was using a helmet made out of non-lead radioprotective material being integrated with lead glass goggles to help protect the lower views.
So taking these 3 potential solutions, we included them in a Q matrix to see which one best fit our 5 design requirements. Taking into account different weights, we wanted to see which ones were best addressing these criteria and which criteria were most important to us for our solution to succeed. So the one that came out ranking on top was our modular blinds, as it was better than the current baseline of radioprotective barriers, it being reducing exposure to radiation, being applied in fast application and time-sensitive procedures, and also minimizing the long-term stress on the physician for the future.
So I present to you the Z-Fold. The Z-Fold is a device that can be implemented by hospitals onto fluoroscopes to protect healthcare specialists from scattered radiation. So essentially, it's a ring-like structure made up of 12 accordion folds that can move up and down as such, and it's automated. this would be attached to the above fluoroscope sensor, and it could descend all the way to the patient on the table. Now, we cannot do this from the prototype, but ideally the actual model, each individual fold of the accordion would be able to be raised and lowered accordingly. So that way, the individual folds could be mapped to contour the patient and the table, completely surrounding the patient and the sides of his body and entrapping and absorbing any scattered radiation. Additionally, each flap can be raised and lowered by the doctor manually, not just automatically. That would allow fast access inside for anything that goes wrong or if he needs to access the X-ray area.
Each pleat in the modular folding device is composed of a triple layer material. The inside has a very thin lead barrier, and the outside are composed of nylon and maxine. Nylon is a fabric that we have seen every day, but maxine is a new and innovative material that has been proven to provide protection from radiation. It is lightweight and it can be woven into all kinds of fabric to increase the scope of its applicability. Additionally, each of the pleats are set in with 3 wires that run down them and are controlled by a motor and winch system in the housing compartment that are attached to the top of the X-ray sensor. And when the winch is rotated, then the wires run up the pleat and the whole system, or one module is pulled up.
This maxine material mentioned by Sam is new and innovative, and potential research that's occurring right now has mentioned that it can be woven into clothing material. So we chose nylon as material as it has both cotton and spandex capability, so it can both stretch, which is really important with the Z-Fold design, and it's durable. It's also effective against shielding radiation up to 8.2 megahertz, which fluoroscopy currently uses around 10,000 to 100,000 hertz of radiation frequency-wise. So you can see that the maxine combined with a thin layer of lead in between the 2 layers will be very effective in protecting any medical professionals in the room from scattering radiation that's occurring off the patient. So the total weight that we're considering, that when calculating the amount of material we're using and the density of the material, is a total of about 5 pounds. This lightweight device is really important with our Z-Fold design because we want the machine to be able to freely rotate without any issues and not be weighed down or have any manual mechanical issues. The size, also fully compressed, is 3 centimeters, which is important so it's not in the way of the doctor if anything were to go wrong or need be access the area that the Z-Fold is covering. Fully extended reaches a length of about 1 meter, and the total price is about $2,800. This, combined with the fact that this reduces the need for any individual radioprotective equipment, will also save the hospital a lot of money in the future.
Z-Fold is the future of fluoroscopy. At $2,800, it's relatively inexpensive, especially when you consider the fact that it's one device that permanently attaches to the machine and seals off the radiation from all the medical professionals in the room. It can be manipulated automatically and manually, so it can adjust as the fluoroscope rotates during the procedure, and we can also customize the conduction depending on the size of the fluoroscope. In terms of future product development, we're hoping that as new materials develop, we can eliminate the need for lead entirely and completely seal off the radiation that's being exposed to the medical professionals.
Okay, judges.
My question is mainly regarding to the size of the device and diameter. Is that a true size prototype? Is that scaled up or down, or what size would the actual device be?
This was scaled down to a diameter of 12 inches, an outer diameter of 12 inches, an inner diameter of 10 inches. However, for the device, it would depend on the fluoroscope because there's not necessarily one size fits all. It would feature a range of size.
And I guess follow-up question to that, depending on the size of the fluoroscope, I assume that's for mounting it to the fluoroscope,
yes.
For the size. In your research, have you seen where is most of the radiation scattering coming from? Is it directly, like immediately around the fluoroscope beam that's coming through and it's detecting, or is it more around the periphery, or like what? Why did you choose such like a narrow area?
Do we have a picture of the radiation? No, we didn't. Oh, we took it out. So the radiation is scattered after it hits the, well, for now, I'll talk about neurological interventional procedures, just for an example. When it hits the head, that's when it scatters outward from the head. if this were the patient, this is the head, it would scatter everywhere this way. This cylinder is made to cover from bottom to top, from the bottom of the head on the table, or a little bit lower from the table on some sides, to the top of the sensor, which is essentially covering everything. Any radiation that would escape this would go down to the floor, which could be easily fixed by incorporating either lead on the floor, some different material, or maybe it'll go in a negligible direction anyway, because if the table were here, the physician is here, and you have technicians, maybe an anesthesiologist and a nurse over there, it could scatter that way, which is not as dangerous as what you typically see.
The basic idea is for the final design of the neurological version of this device to cover the head completely, and for the device to map around the neck so that it's not stopping at the neck and letting the radiation escape to the sides, but some of the modules will map around here while the other modules lay on the table.
Essentially, we designed this device to work for multiple procedures.
So just trying to understand the operations of this one. So is this will be gated with the radiation whenever it is captured the images? Like
Yes.
how will you have the control of this device when a physician is working?
Okay, so we were thinking of incorporating this automatically into the device. The physician and the techs primarily are the ones that move the image sensor.
Correct.
And the device does know where it's going to move. Therefore, we could, if we have 12 individual components in this, we're thinking of cutting it like this. Each one can individually and independently come up by itself, which is why we did 12. It would know which one it would need to adjust to make room for the rotation adjustment it's making while it's doing this. Also, the physician, if it were not to work properly, can manually adjust it as well to make it perfect.
So the box is in the center diagram or where the motors would be for actuating?
Yes.
Yes. Right here inside the housing compartment would be where the
Right.
modules are, yeah.
And so what sends signals to the controllers? How do you integrate that with the overall system?
We were thinking of doing a pressure sensor at the top where we would have the motors as well, which could detect the pressure that it would receive from touching various surfaces, and it would send it back, and then with the movement it would also adjust the height of different independent components.
And the automatic adjusting would keep it off of the surface of the patient?
It would keep it, oh sorry, go ahead.
There wouldn't be any sterility issues?
No, it would keep it barely touching the patient, but it was also priced at $2,800. So if sterility were something that we could not accomplish, it's still a reasonable price for replaceable components.
What about just obstructing the workspace and the sidelines?
Thank you for your question. That's a good question I wanted to address. So for interventional procedures, which is what we're focusing on here for fluoroscopy, neuro especially in this case, the physician, all the techs, and the nurses will never come into, or rarely come into contact with the head of the patient. If need be, they can manually adjust it to do whatever they need to, and it's generally the nurse that would, or an anesthesiologist, which I would also like to note, general anesthesia is very rare for these procedures because you want the patient to be awake. So the physician generally needs access either to an arm, a leg. Generally it's safe to say that they need access to the whole torso, but even though they're working inside the head, they're using the image only, and I would say access to the head is almost irrelevant to the physician themselves.
So this
Okay, well maybe one more.
so this would require modification of the fluoroscopy system. It's not an add-on someone can attach. It has to come integrated with the fluoroscope line.
The idea is to have it as an add-on device that can be implemented at any time. You buy the modules, you buy the software that comes along with it, you hook it up to the machine, you have your computer set up, just another app that you can use to control the device or automate it.
The mechanical aspects of the Z-Fold should be mostly separate from the fluoroscope, so if need be, they don't want it for that particular procedure, they don't have to use it. But the automation system will be entirely in the Z-Fold, so it will be easy to integrate both.
All right, thank you.
Awesome, thank you.
Okay, students, so grab your phones, or I guess that would be what you would need, phones, and is that right? Professor Fred's going to post a QR code. Judges are going to wrap up. All right. Sooner or later, our disco operator here will turn off the music. Thank you, disco operator Fred. All right, we'll do what we refer to as the People's Choice or your peer awards first. For these, please just stand where you are so that we can reward you. The first one is the most feasible solution, and we actually had a tie. And so these awards, you will receive $25 per student for the teams. So the two teams that will, and everybody gets it. We don't cut you down to $12.50 because it's a tie. RDS and Ray-Ban. Okay, our next award, Best Prototype. Best Prototype. I don't know if it's the best. It's the one that required the most work because I watched it happen. Team Z. Okay. And best example of teamwork. Now, this is actually not voted by you because you would never vote for someone other than yourself. This is voted by the Malloy team. We spent a lot of time with you all weekend. I value this one a lot because there are always some dynamics. We had some dynamics this weekend, not as bad as we've seen, but we've had some. It means a lot to be a good teammate. So you should reward yourself. And I'm telling you, this is a skill. And this is not to say that the other 5 teams didn't do a great job, but one team really stood out. This was a comfortable margin of victory for this team. And this is a sort of life skill that will serve you extremely well as you go into industry or research or whatever you decide to do. Best teamwork goes to Aggie MedTech. Let Danny get a picture. You might want a picture of you. I don't know. You guys are so cute. Okay. Best video, which is a repeat winner, Team Z. Okay. And best presentation, just meaning best presentation skills, RDS. Now for our cash prizes and our host, Mr. Hall. Well, I'm actually going to ask, I'm going to put him on the spot. This is the guy that came up with the need statement. This is the guy because he won Problems Worth Solving, which I hope all of you will participate in April. But he is also involved in this industry, right? So he's down at InMed learning to do this professionally and practicing it professionally. So every day, 7 days a week actually, if you don't know the InMed program, Mr. Hall's involved in this. So I'd like to just ask Eric, because he worked as a mentor and roamed around all weekend long, I'd like to ask Eric how he feels about the work that was done this weekend. And again, I'm putting the guy on the spot. He didn't know I'm going to ask him this. Just say a little bit about what you thought.
I was very impressed. You guys worked extremely hard, and I know walking around and interacting with every team, it was phenomenal. You guys were all working very well together. Everyone was doing their part. That was pretty obvious, and I liked hearing your crazy ideas, even if you didn't go pursue them, because I mean that's what makes this fun. You know, you can come up with something like that'll never work. Everyone says it's terrible, but maybe there's like I think we talked about in the intro. There's something that's useful out of that, and you can take that and run with it and combine it with more reasonable ideas. But that's part of what makes this fun. That's why I enjoyed Aggies Invent when I did it a couple years ago, and so I'm glad I could see all of you guys having that same fun.
Thank you. Thank you. Okay. So we had a situation this Aggies event, which we often have. Not often. It's not rare that we have this. We actually had a tie for second place. So what we do when we have a tie for second place is we give both teams the second place award. So we're going to award two $2,500 awards per team, and then one $5,000 award. And Eric Hall is going to actually present you with your checks. So if you would come up when I call your name, and we want some chance to take some photos with you. The first second place team is RDS. Maybe out in the middle here. I don't know, is that good?
Yes. So
take instructions from this, you know, the boss here.
Okay, so can we have the tallest in the back? kind of fill in those gaps. There we go. Sorry. Yeah, perfect. Then you'll be right there.
You don't get the check.
No.
You don't get the check. I actually don't know how it works, but somehow mystically, magically, Mr. Maya will just make the money show up in your account one day soon, like within the next month or so. Okay, our second place team is Comex. Nice job.
We need Professor Fred in this.
Come get Professor Fred. Congratulations. All right. And our first place winner this year, before we announce our first place winner, let me just mention to you before you leave, because this is it, make sure everything's cleaned up. Everything you've had, all your junk. Make sure your stuff's clean. Your mom's not showing up, right? So your mom's not going to be here, so you clean up so that we don't get in trouble with Zachary custodial group and facilities. Also, before you leave, please come and say hello. If you haven't had a chance to introduce yourself, please introduce yourself to the judges. Thank you for being here, but come do it in person. Come meet them. It's another life skill, right? Just say hello and say thank you. Introduce them. Let them know who you are, what discipline you're studying. They don't have anything to do for the next 3 hours. They're happy to sit here and visit with you. I'll be gone. All right, first place winner this year, Team Ray-Bans. Toss it back, and that ain't you.
You hold the top of the check. There you go. Engineer.
One, two, three.
All right. Thank you very much. You are now dismissed. Clean up, say hello, and thank you to the judges. What? Whoa. Or the winning team?
Yes.
Okay, if you won, you are required, it stands between you and receipt of money, to come have an interview with Danny Sullivan. So come right in, she's going to be right here. Come have an interview. All three teams that won the big prizes, come talk to Danny. Thank you.